Welcome to the last session of Dev Summit. Thanks for joining us here. Hopefully everybody got a good lunch and are energized and ready for our last session. I'm Adam Mollenkoff. I'm the capability lead for the real-time and big data aspects of our platform. With me I have Josh Joyner, who's the product manager and product owner for the GeoEvent Server product. We're going to walk through an intermediate to advanced level session today on applying real-time and big data GIS and some of the best practices around that. The only overview slide I'm going to provide is this one that basically talks about that we have ArcGIS Enterprise as a foundational layer for the platform, providing typical GIS services like map and feature services and stream services. And then we have additional functional servers that extend that foundational ArcGIS Enterprise with additional capabilities. Two of those are the GeoEvent Server and the GeoAnalytics Server, where GeoEvent is responsible for applying real-time analysis capabilities to the platform, bringing in data from a wide variety of sensors, and then being able to disseminate alerts and notify people about patterns of interest when they happen. The GeoAnalytics Server is all about running parallel computation or parallel analytics using Spark as a framework internally to run really fast analysis on really high volume amount of data that's typically been stored in the spatial temporal data store. But it also can work with data that's inside your organization. If you have Hadoop or HDFS or Hive or those types of systems, it can connect to those, or if you just simply have folders full of delimited text files or shape files, it can work with those as well and bring that data into the platform. The spatial temporal big data store is kind of the glue in between those. That's not a product, whereas GeoEvent Server and GeoAnalytics Server is a product. The spatial temporal data store is a component of the platform that comes as part of the ArcGIS Enterprise. And you can deploy one or more machines that have the big data store on them to have a distributed database. And this allows you to store not only high velocity data of data that's coming in very fast, but you can also store high volume amounts of data over time. And we're going to deep dive into the purple and the orange aspects of this platform as we go through the sections here. So as a quick agenda, we're going to go through architectural recommendations. So what do you need to consider when you're planning a deployment? What are the resources that are most important from a compute, memory, and storage perspective? We'll talk about big data storage, in specific the spatial temporal data store and some of the best practices and how data reliability is achieved with it. And then we'll talk about performance, resilience, and scalability. If you've been to any of these best practices sessions before, the first two sections are similar to what you might have seen before, but the rest of the sections are entirely new with the 10.6 release. So stick around, you'll see a lot of new content coming in section 3 or so. Stream services is another important aspect of a real-time GIS system. That's what allows us to push data directly up to clients with really low latency. And then we'll talk about GeoEvent service design considerations. So how do you configure and the best ways to do real-time analysis. And then finally, upgrade planning, moving from one major release to another, and then also how to go about troubleshooting real-time and big data systems. So first topic is architectural recommendations. And so these are in order of what I would deem as kind of most important factors when you're planning a real-time GIS deployment. So the operating environment is super important. We typically test and benchmark on M4 2X large machines. So that's like an 8 virtual CPU machine with 32 gig of RAM. And we've gone to a lot of different customer sites where they're struggling to achieve the same performance that we've benchmarked. And so what we found in a lot of these circumstances is that they are using like VMs and like a Citrix environment or something of that nature. And so VMs work in a way such that they share the hardware across many applications. And if you're running on the same machine physically, the other apps are running that are also contending for the same types of resources, we see kind of degraded performance in some of those cases. And so in some cases you don't have control of this and you have to operate in that environment. So what's super important is to make sure you benchmark your solution and make sure that the quality of service is going to be able to be met with how your environment is running. If you're and when I say virtual machines, I'm not meaning like Amazon or Azure. So if you're using Amazon or Azure, those are also virtual machines and a cloud infrastructure, but those have much better isolation capabilities. And so we get extremely great performance on Azure and Amazon and things of that nature, or Google Cloud or whatever cloud that you choose to use. If you have a need to bring this on premise and you can't make use of a public cloud infrastructure, dedicated bare metal machines are definitely the way to go. If you can use public cloud instances, those work just as well. But you want to make sure you have a deterministic environment. It's not that today things are working well and tomorrow some other app in a virtualized environment landed on the same machine and now I'm not getting the same performance I was getting before. So make sure if you can control that to isolate yourself as much as possible. The next most important aspect of planning a real-time GIS deployment is the network. And so we suggest at least a 1 gigabit per second network speed. So if you're able to achieve that inside your organization, which most folks can, definitely do that. If you're working in a cloud infrastructure, you can choose the instances that allow you to do even higher than that. So 10 gigabit per second is very common in Amazon and Azure as well. So obviously being a real-time system, data is coming over the network into the system and also emitting out of the system as well with stream services and other things. So the network is a very important factor for this. The next most important factor is memory. And so if you're working with public cloud infrastructure, just choosing the right amount is really all you have to worry about. But if you're working with a bare metal machine, you also need to think about the type of RAM that you have. Is it DDR2, DDR3? We've seen factors of 50% performance degradation between DDR3 and DDR2. And so while we benchmark things to be able to do thousands of events per second, a customer that has an older type of memory, we can see factors less than that. Also, the clock speed and the transfer rate of your memory is super important as well. And where memory comes into as a factor is when you're doing stateful things with your real-time GIS. And so if you're working with geofences and you're detecting an enter or exit condition, we need to keep in memory the last known location of a track to know that it was outside and then inside of an area or entered or exited. Also, there's other calculators like motion calculator and other things that make use of state as well. So if you're doing any type of stateful processing in your real-time GIS, you need to consider the memory. And then lastly is the processors. So the number of cores that you have available is an important factor as well. And so you can vertically scale up on a machine to have 16 or 32 CPUs, and that works just as well. Consider the licensing needs for that when you do that. But the number of cores certainly will allow you to vertically scale, but you can also horizontally scale, as we'll go into in a bit. And then the last factor here for the GeoEvent Server aspect is the disk. And so disk hasn't been as important prior to the 10.6 release as it is at 10.6. And so we make use of a new component at 10.6 called a gateway, which we'll go into later on, that basically allows us to have more resilience of data coming into the system. And so if for some reason GeoEvent Server as a process stops, but data is still flowing in, when GeoEvent Server comes back online, we can pick up where it left off without necessarily losing messages. And that's a new capability at 10.6, which we'll talk about as we go further in this deck. But given that capability, the data that gets queued goes onto disk. And so each input that you have can store up to about 600 megabytes of disk space. And so if you have 30 inputs, you need to factor that, the maximum of that would be 30 times 600 megabytes of disk space. And so you need to factor that into your planning when you plan your hardware deployments for this. So we recommend a 10 gigabit minimum, and this is, as I mentioned, a new requirement for 10.6. On the big data store aspect of things, the operating environment, again, is the most important factor, similar rules as what we talked about before. But then the disk would be the next most important factor. So depending on how fast you want to write data and be able to query data out, the faster the disk, the better. If you're on the cloud and like Amazon, if you choose EBS optimized, that will give you the best performance. If you're working with bare metal machines, then obviously choosing local SSD is going to be faster than a spinning disk option. And so the size of your disk is very important as well. So we need to look at what your data retention needs are and how long you want to keep the data around. What the rate of the data coming in is, and how big the data is. And so given that, you can figure out, do I need just one instance of the big data store, or do I need multiple nodes to do that? And should each one have a gigabyte or 3 gigabytes or terabytes of disk space across those machines? So that'll help you plan out how to do that. And then the network is important, as for the same reasons we mentioned before. Memory is also important if you want really fast query capability. And so the spatiotemporal data store makes use of keeping data hot that was recently accessed. And what I mean by hot is that it keeps it in memory. And so if you access a feature service and nobody else is hitting that system and you access that feature service again, it's going to have a lot of hits and cache. for that, and that's what gives it some of its quick response time. But even if it has to pull it from disk, it's still very fast given all the indexing and everything else that happens. And then the processors are important here. So if you want fast query response time and you have lots of people hitting the system at the same time, the more memory you have, the better, and the more processors you have, the better. A couple notes on memory is that 16 gig is the minimum that we recommend. But we recommend if you can do a 64 gig system, then you can allocate 32 gig to the spatial temporal data store, and that will give you the best performance possible and the biggest cache size of hits for customers. So as far as topology of what does this look like when I deploy an environment, minimum environment that would be a real-time GIS system would look something like this, where there's 3 machines. And it's important to make sure that these machines are isolated because these functional servers have very similar resource needs. So if you were to, GeoEvent Server is very network and CPU and RAM intensive. And so if you put that on the same machine as the big data store is also network and RAM and CPU intensive. And so if you put those on the same machine, they're gonna be competing for the same resources. And so if you have, certainly in a development environment, that works great. And you can prove that things work functionally. But in a production system or a staging system, you'll want to separate those concerns so that you can get the best performance possible. And then ArcGIS Enterprise should obviously be on its own machine as well. And Enterprise would be server, portal, the web adapter if you choose to deploy that. And that would allow you to keep those services deployable. An optimized environment would look something like this, where you might have some data reliability guarantees that you want to make so that in the previous picture where we only had one node of the big data store node, if we lost that disk, you might lose that data. And so if you want to make sure that you're not losing data and that you have continuity of service, if clients are still connecting to the spatial temporal data store and accessing feature services and map services and one of the disks fails, we can actually, if there's a multi-machine setup like this, ensure that the results are exactly the same, even when there's a disk failure. And we'll walk through some diagrams that explain how that works in just a bit. So a minimum environment with big data deployments would consist of also a geoanalytics server. And geoanalytics is, as I mentioned before, what allows us to run analysis in a parallel way across data that's in the big data store or data that's on the right-hand side from your organization. And then an optimized environment for both of these might look something like this, where we have a multi-machine site for GeoEvent, a multi-machine site for geoanalytics, and a big data store that consists of about 3 nodes or so. And so this is about 10 machines to deploy this. And so this becomes a bit challenging to set up and install and do things with. And so over the last year and a half or so, we've introduced these cloud builders that allow you to build these environments very quickly. And so if you can make use of public cloud, this is a very quick way to deploy this type of environment. And this works in an autonomous way where you just specify the instances that you want, the number of machines you want, and it'll go spin these up for you. That's true for Azure, but it's also true for Amazon as well. And on the left-hand side, you can see the little castle-looking thing there is Amazon IoT. And so we pre-configure these to be able to have Amazon IoT and Azure IoT available when you deploy to these types of environments to bring data into GeoEvent Server. The next topic, I'm going to deep dive into the spatial temporal data store. So as I mentioned before, an optimized environment might look something like this, but I wanted to kind of demystify why would I need to have multiple nodes versus one node? So the first reason is what I already mentioned before, if there's a disk failure and you want continuity of service. The other reason might be that I just want to have a data retention rule that says I keep this data around for 6 months and I'm accumulating 1,000 events per second, and those are too large to store on one disk physically. And so you might want to spread the data across multiple nodes. And so the way that works is if we expand this picture here, if I have 5 nodes in my deployment here, GeoEvent Server is going to be listening for real-time data and writing that data out to the big data store node. There's this thing called a replication factor, or this R equals 1. And so per feature service that you write to, you can specify the replication factor. The default is 1, which means every time we write data to a node, like T1, T being the track 1, it writes a secondary record to a secondary node. And so this allows us to have redundancy of the data. And then likewise, if we store a track 2 and a track 3, and if we had millions of tracks, there would be millions of primaries and millions of secondary across the cluster of big data store nodes. Now, if there's a failure, like this machine up here on the top fails for some reason, the disk fails, or the process dies, or something becomes unrecoverable, what happens is that we need to promote the secondary T1 to become a primary, and then we need to establish a secondary for T3. And so the way that would work is that node 4 that had the secondary before would become the primary, and then a secondary would establish somewhere else left on the cluster of machines. And then T3 would be a secondary on node 5. And so it doesn't really matter where these land, it just matters that we have a quality of service that says there's always a secondary copy of the data. And so this is how it works, that even when we're in this state right here, where we haven't established the transition of the data, we still, while people are querying the system, can give consistent results. And so there's no kind of temporary failure or anything like that. And so if you want to make sure that your data is reliable, you can keep our default setting of replication factor 1 on the feature services. If it's not of importance to you, maybe it's data that's okay if you lose some data every so often, you can set that replication factor to 0, and you'll get slightly better performance. If you want to make really darn sure that you don't lose the data, you can increase the replication factor even higher than 1. So if you had a 5-node system, you could say replication equals 2, 3, or 4, whatever reliability you want to have. So that will affect your write throughput performance, because in practice, if you're writing with a replication factor of 3, then you're writing a primary and 3 secondaries. And so it's going to basically be writing 4 events for every event that you get in. Another thing is that we automatically set data retention policies on the big data store feature services that are put there. So you can specify a feature service data retention policy of a certain time period, so 6 months or a week or a day or whatever you want that to be. And so we will automatically purge data out after that time, so you don't need a DBA to go in and clean these things up. And this being a managed data store, as part of our ArcGIS data store solution, we provide that capability as kind of a black box thing to you. You just configure your retention policy, and we take care of that for you. Additionally, when we index data across these nodes, we're indexing the data by space, by time, and also by all the attributes. So we apply a reverse or an inverted index on all the other attributes that are on the data. And so these indices are available on each of the nodes for the data that's primary to them and also secondary to them. And so there's a rolling index option that allows you to set how frequent the indexes roll. And so this is kind of an internal thing, but what's important to configure as a feature service level thing is that if your data is coming in every second and you're getting lots of data all the time, maybe you want your indexes to roll every hour or so. That way, if you schedule it for once a day, then there would be a whole lot of data in one index and you would get slower response times when you query the data. So you want to set the rolling index policy to be equatable to what your velocity is. So if it's every second, maybe hourly is good. If it's once an hour, maybe daily is good for your rolling index option. And if you're getting data in just like once a week or something, then you could set this to like monthly. And so typically hourly is a good setup because most real-time systems are coming in every second or so. The last point here on the big data store, the second to last point here is snapshotting. So in addition to the replication factor that we have, a lot of our enterprise organizations gave us feedback to say, I want additional reassurances that if the entire cluster fails for some reason, I want to be able to resurrect it and not lose the data. And so we do allow you to configure snapshotting capability. The default is once a day, but that's not turned on by default, so you have to go turn this on. And so that snapshotting would happen once a day, and it snapshots the entire state of the cluster. So if you have a system that's been in place for a few months and you go turn snapshotting on, the first snapshot's going to be really large, but every snapshot after that will be incremental. And so each day there's an incremental snapshot that's taken, and then if for some reason this entire, all 5 machines failed at the same time or became offline, then you could be able to restore that by setting up another cluster and saying restore from snapshot. And so that gives you additional reassurances of the data. And that snapshot can go to S3, it can go to Azure Blob, or it can go to like a network file share or a Samba mount. So that's the best practice for that. You don't want to put the snapshot on the machine where the big data store is, obviously, because if the disk fails, then you've lost your data. The last comment about the big data store here is data can be coming in very fast, and so we store data with an object ID strategy by default that's an int64 strategy. So this is interesting for a number of reasons. One is that int32 is what all of our pro and desktop and ops dashboard, at least the WPF version of ops dashboard used previously. Now ops dashboard is JavaScript based, so it no longer has this same constraint. But what's interesting about this is that even if we get a modest amount of data in, like 1,000 events per second, that's about 86 million events per day. And so we'll run out of int32 object ID address spaces in about 25 days, which is not very long. And that's a fairly modest amount of data. And so we default to int64, which gives us this 9.2 quintillion address space. And so the recent ops dashboard that's JavaScript based and all the web app builders and the web maps and all of those things make use of this capability. And that you won't run out of int64 for quite some time. So I think we'll be pretty good with int64 here. And then there's also a last option too. If you don't ever want to run out of address space, you can use an object ID strategy that's unique string ID, and that would never run out. So this is important to note because when we released the big data store at 10.4, we had lots of customers that took this on and said this is working great. And then about 25 days into it, we had a number of customers saying, every time I open this feature service up in Pro crashes. What's going on? And so it's exactly because of this reason that the int32 ran out of space. And so whenever we had an object ID that was bigger than int32 and you try to load that into Pro will just simply crash, or runtime apps will crash. And so just be aware of that. So int64 is the default, but know that those clients are going to be constrained. If you don't like that situation, please communicate that feedback to the Pro team and other folks so that they can prioritize efforts to get this on. It's not a small task for them to move things to int64, so they need to hear customer feedback about that. So just be aware of that as a constraint. And with that, Josh is going to walk us through some of our latest and greatest performance, resilience, and scalability efforts that we've been doing as a team.
Thanks, Adam. So not surprising, performance is typically some of the first things that we hear about from customers. It's a priority for users when they're trying to determine, can I actually handle this solution? What kind of velocity am I going to be able to support in my given environment with the data I'm working with? Thankfully, we've been able to actually increase the throughput for GeoEvent Server with every release, going back to 10.2, where we were able to support 500 events a second, up through the 10.5 release that we did last year, which was 4,000 events a second. Now with the new 10.6 release that we released in January, we were able to increase it another 50%. So the new architecture now allows us to support upwards of 6,000 events per second. And that's based on bringing data in from TCP and writing out to the spatiotemporal big data store. That's not just sending data in and sending it out to some external source. We do provide, and we're in the process of preparing and kind of cleaning up our test harness and making the sample data that we used for benchmarking this available on GitHub. We were really hoping to have it ready for you guys this week, but it wasn't in a state where we could hand it off yet. We're hoping to be able to put this out on GitHub next week. And what we'd recommend doing, if you guys don't already follow the blog on GeoNet, that gives kind of information about kind of best practice stuff. We update on that blog regularly. This is the link to it. We'll make an announcement out on that site once the GitHub site's available with that testing data. And it's really probably a great first start for users working in this space to be able to go and test with the exact same data that we use, the exact same testing harness, and kind of benchmark your environment, because then everything else downstream kind of can be based off of your performance in your environment. Again, all of our testing, just to kind of a sneak peek in that, all of that's going to be done, that we've done, has been on Amazon machines. That's all on M4 2X large machines. So these are commercially available. These aren't some special Esri special machines. You can just go get the exact same machines if you need the exact same performance. So one of the other big things about real-time capability is we've had a lot of requests from users over the years to be able to provide kind of greater resiliency. So similar to the high availability type deployment scenarios with Portal and the GIS server. And with the 10.5 release, that was available only if users would bring their own gateway. Effectively, the best practice would be for you to install and deploy multiple siloed GeoEvent sites. So if you wanted 3 machine setup, you'd basically have 3 mirrored installations of GeoEvent Server, each of which with the exact same configuration. You'd have to set up some sort of gateway on the front end of that. We had a tutorial that kind of walked you through this process. It used Kafka as an example, as a kind of a message bus on the front end, but you could have brought, RabbitMQ or ActiveMQ, some other kind of different front end message bus in that place. The challenge with that was, as I mentioned here, kind of the barrier to entry was really high. We had a few customers that were able to do it themselves, but for most customers, in order to really get this successfully deployed, it required some sort of professional services engagement, some sort of support from some of our staff here at Esri to help users get this deployed in their environment. And the other challenge with it is you kind of lost all flexibility with it. So, one of the nice things about GeoEvent Server is you have out-of-the-box, connection to like 20 different types of data feeds, and you have these add-on components to the gallery that let you connect to different third-party vendor feeds. But when you went with this solution, with say Kafka, for example, you were responsible for getting all of your data into Kafka because that's the only method that we were able to communicate with to bring the data in. So what we did with the 10.6 release is we tried to take some of that same functionality that we documented previously and productize that. So we created a component called the GeoEvent Gateway. This runs alongside the GeoEvent Server Windows or Linux service. It's designed to just be turned on and left running like a file system. It handles the communication between multiple sites for you. So you're able to follow a similar deployment pattern to the ArcGIS server, multi-machine site deployment. You can get on there and you can set up as many sites as you want to add. And we handle on the back end message distribution between all of those participating sites for you automatically. The nice thing about that is it provides the additional kind of failover resiliency if a machine were to go down, similar to the data storage solution. If you have input running on 3 machines and one fails, you're able to continue to have data coming through. One of the other nice things about it is that we were also able to see improved scalability and performance as well. Performance was able to scale linearly. So if you wanted to have 3 machines, you're able to scale up to 18,000 events per second potentially. If you had 5 machines, you could configure it such you could get 30,000 events. This is able to scale. 5 machines is probably the practical upper bounds of what we'd recommend trying to deploy. You can go a little bit beyond that, but that's starting to get more than most people are going to want to have to set up themselves, even with the cloud builder that Adam showed earlier. We did provide, this was set up last weekend, a tutorial specifically on how to set up multi-machine sites using GeoEvent Server. This is available at the link below. This provides all the normal instructions you'd expect for setting it up. And also, I think a really important component is included with this as well that shows how to utilize some of the Kafka tools, Kafka being one of the components within that gateway, how to use those tools to go in and kind of see some of the site health, particularly the actual Kafka cluster itself. You can get in there and kind of check to make sure everything's communicating properly. Our long-term plan is to take a lot of those kinds of tools and embed them in the product directly. But in the interim, this is kind of the fastest way to get in and kind of give you that insight as you're first getting started with that. So we're going to kind of shift now to talk more about kind of factors that can actually impact your performance. So not just the fact that, what the potential architecture can do, but really about, the impacts of how your services are configured. So this is a very common service example you might be working with. In this case, we have 2 inputs here on the left-hand side. For this example, each one of these is importing about 1,000 events per second. 2 slightly different data types. And in this example, the first thing that's going to do is it's going to send those through some sort of spatial filter. Maybe we're looking for only those events that occur within a given area. In this case, it's those that have geometry inside a specific zone. So assuming all of those events were to match this geofence, and all of them were in this area, you'd potentially now have 2,000 events per second going through. So, you know, it makes sense. You had 1,000 for each one. They're both going to the next step. You got 1,000 going through. Well, then the next step in the process, because there's some different operations that need to occur on each of those two different input types, would be putting a filter in place. So on that top track, we're filtering just for data of the first type. And so going into that filter, we effectively have 2,000 events going to that filter. It's going to pull out the ones that it wants. It's going to send it on its way. We have the second case at the bottom. 2,000 events are going to the filter. The filter looks for those events with a certain pattern, and it's going to send those on. So again, assuming everything's coming through and we're back to the initial 1,000 events, that means each of the next step is getting 1,000 events. So that buffer is getting 1,000 events. This geotagger processor is getting 1,000 events. The motion calculator, that's one of our add-on components from the gallery, that's getting 1,000 events. So by the time it gets to your output, you now have 1,000 events going to each of these three outputs. So the point of this is that the input counts don't always tell you the whole story, because while you might have had, 2,000 events coming through a second, oh, my data, it's only got 2,000 events a second, and the folks at Esri said I can handle 6,000. This is well within the expected range. I can actually set up a couple of these. I can run a couple of these in my system. And so, okay, 2,000 events a second coming in. But just looking at the output, we already know you're now sending 3,000 events a second out. So that 2,000 incoming doesn't tell the whole story. But the really interesting part is this middle section here, because in the middle of that service, you're actually sending 4,000 events a second, up to. So if you're trying to scale a system based entirely around the incoming counts of data, you don't see the whole story. And so it's really important when you're setting up your service to kind of think through the methodology of, what's the worst case scenario with this service configuration? If all of the potential data would be coming through, how's that going to affect my throughput? So if you were banking on, running 3 of these types of services on a machine that could run 6,000 events a second, it's not going to happen. You're basically going to run one service, and then you're not going to be able to kind of run anything else within this system. Adam mentioned earlier about the importance of being able to kind of have sufficient allocation of memory for these systems. By default, the GeoEvent Server is only allocated 4 gigs of RAM for the JVM process that's running most of this back-end technology. If you want to have more, and we highly recommend having more, there's the configuration file you can edit within the ETC folder. It's the ArcGIS GeoEvent.config file. And this is where you'll see all the different parameters for modifying the JVM process. And in particular, you'll want to modify the parameter that allows you to set a maximum Java heap size. And so you can go potentially up to 32 gigs for that. Setting more than that is, you're not going to have any, it's not going to be efficient, because the JVM, that's a JVM functional limit. So that's about as high as you're going to want to go. Another concern is potentially the quantity of unique track IDs. So if you're bringing in a data type that has more than 1,000 unique vehicles or sensors, it's important to know that out of the box, GeoEvent is only designed to handle 1,000 events, 1,000 unique tracks. This can be configured very easily by going into, there's another file in that ETC folder that allows you, it's the service manager configuration, and you can increase the cache size, how many different unique tracks it'll store in cache. If you are going to do that, in particular if you're going to use it with the incident manager, there's some additional settings in the global settings tab that you'll also want to increase to whatever that same number is, so you can make sure that it's that potential new threshold is utilized in all the tools correctly. So there's some other concerns and qualifications when you're working with stream services and scaling those, and so I'll hand that back to Adam to talk through those.
All right, thanks, Josh. So stream services, I'm going to get a little technical here, and I want you to understand kind of what's happening underneath the hood so you can better understand how data passes from GeoEvent to stream services and some of the effects it might have on your clients. So we're going to start first with the 10.5 picture, which is probably where a lot of folks are still at as far as a deployed production environment. And so, as Josh mentioned before, we did not have a multi-machine site capability at 10.5. So if you stood up more than one GeoEvent, it was a siloed site scenario where you had the first GeoEvent in site 1, the second GeoEvent in site 2. And so those two machines don't really know anything about each other. And so the interesting thing here is if you did stand up that gateway in front of the GeoEvents, which was a manual process, as Josh mentioned before, then that data would pass through and one of those GeoEvents would get that event, and that stream service would pass that data to whatever clients were connected to it. One of the limitations here is that only client A and client B got that event, and if the second message came through, the second machine might have picked it up and only client C and client D saw that message. And so if you configure this type of environment at 10.5 and you try to put up this resilience setup at 10.5, be aware that there's some constraints here. Now this can be resolved so that when you're using the Kafka input connector in GeoEvent, you can configure it just through configuration in GeoEvent to say use different consumer groups. And if that's the case, then the GeoEvent will actually get both of those events simultaneously, which is what you would desire from a stream service perspective. But be aware that if you do that, as those events are passing through, you're also duplicating the analysis steps that you're doing. So if you detected some pattern of interest and you wanted to email somebody important in your company when something happens, they're going to probably get 2 emails. And so you have to consider that as a constraint. That's a new constraint that you've introduced by making this perform this way. So neither of those are good answers for deploying an environment like this, and then the second event would pass through obviously as well. So what's good news is at 10.6 is we've productized all of this and hidden all those details from you where you don't necessarily have to worry about that anymore. So the first thing is you don't need to worry about the gateway. When you install GeoEvent on machine 1 at 10.6, we automatically install a gateway for you. It's a transparent thing. You don't need to specify anything at install time. You don't ever need to really know about it. Just know that it's another process that sits in front of GeoEvent at 10.6. When you install the second machine, you add it to the same site, those gateways automatically start communicating with each other. Again, you don't need to do anything with the gateway, it just works. And so at 10.6, on the ingress, all clients will see all the events by default. So if that event comes into GeoEvent, and now we have all the flexibility of all the different input connectors that we had before, that event will be distributed across multiple stream service instances, and that's done through this thing that we have that's in another internal detail called RabbitMQ. And so RabbitMQ is another messaging system that we use such that when an event passes through here, we can inform other stream service instances of that event, and that event can pass over to all the clients. So the good news is all clients see all the data, which is what you want from a functional perspective. And then as 2 comes through, that would pass through, and we would populate that across the other things. So stream services work really well at 10.6. The other thing that you might want to consider when you're planning a stream service environment is you might not necessarily want client A, B, C, and D to necessarily know the details about what the DNS names are or the IP addresses of your GeoEvent services. In that case, you might want to stand up a reverse proxy that sits in between the clients and the server such that they talk to the reverse proxy and they only know one address. And the reverse proxy is responsible for communicating with the services downstream. And so what that would look like is the data would pass through, same thing that we saw before, but now if there happens to be a failure on one of these machines, the stream service runs within the GeoEvent process as well, so it would disappear as well. And so you might have had clients that were connected to that stream service 2 that just disappeared. But the good thing is if you have this type of environment, those clients would automatically be redirected to stream service 1. And so you don't need any logic on the clients or anything like that to take that into effect. So reverse proxies are allowed at 10.6. Nginx and Microsoft's application request routing tool are both valid options for you to deploy this. If you went to our Road Ahead session yesterday, you probably heard us talk about how we want to productize this as well. So this is kind of the same pattern as what we had for the ingest side with the gateway before, where you had to bring your own gateway. Well, at 10.7, one of our major epics that we have planned is to productize all of this as well. so you no longer have to bring your own reverse proxy. And that actually brings us a lot more advantages as well. The last piece here is that at 10.7, as the data comes across, our plan is to actually productize this gateway such that instead of that data going to that RabbitMQ component that was there before, we just reuse the gateway to do that as well. And so that will increase the performance of stream services because that RabbitMQ component made the data leave GeoEvent and then come back into GeoEvent again to be communicated. So this will be improved performance at the 10.7 release. And as I mentioned before, we're looking to actually productize the reverse proxy part of it as well. Josh is going to walk us through some more GeoEvent service best practices now.
Thanks. Thanks, Adam. So in terms of kind of service design considerations, we looked at an example earlier that was kind of showing how input can the initial input can actually increase depending on how your service is designed. This is a slightly different example we want to look at here. So in this case, what we have is on the left-hand side where we actually have two services here. On the left-hand side, we have a single input that includes 3 data types. This is a pretty common scenario. We have a lot of vendors that will provide multiple data streams within a single input. But in order to do that, then it requires you to possibly put some sort of filtering to be able to pull out different types of data from that single ingest type. So in this example, we have that same story. We have input coming in that has data type 1, 2, and 3. You have that data flowing to 3 different filters and then to 3 different outputs. In the second service on the right-hand side, we actually have 3 times the inputs, but it's writing straight to the service. So, as you're trying to design these services, it's important to think, okay, which is the more efficient, which is the better designed service? Well, between the two, this service on the right is actually a much better service. Even though it has 3 times the number of inputs, the problem with this service on the left here is really this branching. It's when you try to send that data to each of the individual branches downstream. So let's say, for example, with the example we showed earlier in the day where we had each input having 1,000 events for input, if we had that same one again, we might have 3,000 events coming in over inputs 1, 2, and 3, where all 3 of the data types are coming in. But because we're having to send each of those to each of the filters, you could potentially be having 9,000 events trying to get sent to these filters, which would be a functional constraint and beyond what the product can handle. So it's really important that when you do put in these types of branching within there, realize every time you branch a feed, you're potentially sending all of the data at that previous step onto each of those branches. So we touched on this a little bit earlier. But really, whenever possible, whenever you're designing your services, if there's any kind of pre-filtering you can do on that input, do so. It may seem counterintuitive to need to have more inputs, but it's going to make for a much more efficient service design further downstream. So here's another kind of example that kind of really looks at the types of connectors and the types of processors being used. So for this example, we're using the same input and the same output potentially on all these, so there's no difference on the data, no difference on the velocity, but they're going through a different set of processors. So on the top service here, we have data coming in, and it's going through a service area calculator. This is a component that's available on our gallery. It lets you do kind of drive time analysis based on some incoming geometry. The second service, we have the same data that's going through a field enricher, which is doing some local kind of enriching of the data off a feature service. It's going through a field calculator, going through some intersector, maybe comparing some the local incoming geometry with the geometry stored in your geofences. And the third service, we have our input going out to a projector where it's changing the coordinate system on some incoming data, changing the spatial reference, maybe simplifying the geometry, and then going to an output. But when you try to look at these and say, well, which is the most efficient service? Which is going to be the fastest? Which is going to be the slowest one in terms of kind of the performance impact? Well, it might be surprising. This first service with the additional steps is actually the fastest of the services. Because with this kind of configuration and these specific tools, Each of these are all just using the local service cache. There's no need to call out to any other service. It's all stored in memory. So even though it's going through several processors, it's just a very efficient, very fast flow of data coming through. The second service actually has to utilize the local ArcGIS server's geometry service. So it's having to make a call over REST where it's sending the geometry out to the local ArcGIS server. It's trying to modify that geometry. And these can typically be pretty quick. These typically don't have a lot of performance hits on your system. But if you're using some more complex geometry, if these were, if you were testing the same velocity of data off points, polylines, and polygons, the polygons are going to take a lot longer just because of the potential complexity of the geometry. And that third service, A, even though it only has one component, that has to utilize a network analyst service to create that drive time polygon. And for a lot of cases, depending on the complexity of that network, it could take several seconds for a single response to come back. So instead of several thousand of events per second, now you're looking at one event per several seconds. So it's important to kind of really take a deep look at the types of components you're going to be using as a part of the service as well, and considering the impacts of those choices. Just some other kind of best practices I want to kind of leave you with here as far as service design. Whenever possible, try to configure any kind of filtering or field reducer processors. Try to put them as early as possible in the service. The more data you have flowing through your design service, all of that data requires additional resources to be processed. So if you know there's only certain fields you need out of this data, reduce it, throw it away. There's no point in spending the resources trying to process something you're just going to get rid of a few steps later. So put those filters as early as possible in the design config in the service. Also, whenever possible, try to avoid managed definitions. Almost all of our processors will allow the server and the user to automatically create definitions for you. So if you're wanting to run a buffer processor, something that's going to add a buffer around your incoming geometry, you can have it automatically create a new geometry field for you, or add it to a new field. But by doing that, those definitions are all system owned by that processor. So if you were to later go back and edit that processor, it could potentially delete the definition it created earlier and replace it with something else. And if you have a complex service where you're expecting a certain definition to come through at each step, you could potentially break your entire kind of service model because you were reliant upon those definitions. The best way to do it in that case is really to if you have to use system-owned definitions, make a copy of it, modify it as you need, and then go back and use your own definitions instead of those system-owned ones. Also, if you're going to be writing data out to a feature service, whenever possible, try to import the definition in from that source you're trying to write to, and use a field mapper to make sure that your incoming definitions kind of match up with your outgoing definitions. This is a very, very important component and a very important thing when any kind of service design. I want to touch briefly on upgrade planning. This is something we frequently get requests about. What are some best practices for upgrade planning? Whenever possible, try to do a clean installation of GeoEvent Server. GeoEvent installs in about 3 to 5 minutes. It's not Portal. You're not waiting an hour for it to finish loading. Whenever possible, use it as an opportunity to go in and kind of do some housekeeping. If there's components you don't need, try to remove those. But then export your configuration. If there's any global settings you need to modify, export those as well. If you did any of those changes to the configuration files that I showed you earlier, while you can't just copy and paste those configuration files, you can certainly take note of any parameter changes you might have made. And then, when you do the uninstall, go through and make sure it's really pulling everything out. Make sure it's removing some of the contents, maybe the old configuration. If you're on a Windows system, particularly at the 10.5 level, going from maybe 10.5 to 10.6, go and check to see if it left any components of that old configuration. If need be, you can kind of manually delete those files. And then install the new version, import the configurations, and you're good to go. Really, this is probably more of a concern for Windows users than it is for Linux. Linux handles upgrades in place a lot nicer than Windows does, surprisingly, and a lot of that's just the way the file locks are. So something to kind of keep in mind when you're working through that. Want to kind of leave you with some kind of troubleshooting steps as well. Even the most perfectly designed system is inevitably can kind of have service design problems or other issues. So I want to kind of give you some really places to get started if you kind of encounter some of these issues. From an input side, we get this question a lot. I can't get my data to come in. And this is really the first challenge, probably the biggest challenge users have for GeoEvent Server is, I have data coming from this vendor, how do I get it in? First and most important step is check that definition. GeoEvent is designed to enforce a strong definition. We need to make sure that what you're bringing in matches the schema of what we're expecting it to have. And so, most of those problems are really related to some sort of misconfigured schema. It's a field name is off, a data type is off, maybe it's got some sort of group structure that we're not expecting. And so I know this may sound like, backwards of what I told you a minute ago, but in this case, let GeoEvent create a definition for you. If you can't get the data to come in with the definition you're expecting, let it generate one for you, turn on that option, see what it creates. If all of a sudden your data's working, great. In that case, what you're probably going to want to do is, go back and check that definition, manually edit if need be. If it's brought in data type as a double and really it should be a date field, go within and make those little changes. And then you can always go back to the input again and tell it to say, no, don't create a definition. I want to pick one off my list. So it's a pretty easy process and a very standard workflow for that. On the output side, we see users with these problems too. I got data coming in, but I can't write my data to my feature service, this other vendor site, some sort of input. This sounds repetitive, but check your definition again. Most output problems are due to misconfigured schema. This is so important. You have to make sure that you're using the right definition all the way through. And I know it sounds kind of simple, but it really is the source of most problems that users encounter when working with this data. As we mentioned before, whenever possible, try to import the definition of the service you want to write to. If it is going to be coming from like an Esri feature service, when we import that, it'll include some of those additional reserved fields, object ID, OID field names. I would recommend removing those out of the definition because we can't write to those fields either way. And it'll kind of make life a little bit easier for you. And if you're not already using it, I highly recommend using the GeoEvent Logger application. This is an application that only runs on the Windows deployments of GeoEvent, but if you have a Linux machine, you can copy it over onto a Windows box to use this component. It's basically a TCP interface that allows you to see what data is coming through in real time. And perhaps most important is this first field here. This first field tells you the name of the definition that it's using at that point. So if you have a service that's going through multiple types of processors, or maybe it's changing from a different GeoEvent definition at steps, this will tell you wherever you connect this output to what definition it's using at that point. So it's a great way to kind of validate your data that you're working with. Occasionally, when you're just working with something, it just doesn't work. I've connected it all. Everything seems to be working right, but it just doesn't seem to work. Check your logs. I know a lot of people have had some challenges with the logs, and I think part of that is because the way we handle our logging is a little different than server, but I'll kind of walk you through how that works. Thankfully, for most critical problems, it will just kind of tell you the source of the problem right there in the log. You won't have to go in through any additional steps. It'll tell you where to go. But if you get an error that's a little more generic and you're just saying, okay, a consumer thread was interrupted. Well, I don't know enough about that. I'm not seeing any more information. You can go into the settings, and this is you click on the settings button, and you can actually select the specific logger. So the first part of that log error we saw above that's highlighted, that's the name of the specific component within GeoEvent Server that encountered an error. And unlike the logs within server and portal where you have to set the entire system to debug or verbose for logging. With GeoEvent, you can actually select the individual component that was reporting an error, and you can choose to set it at a higher level. And typically, once you've set that to a higher level, go back and redo whatever test you just ran, and you're going to be able to get a lot more information about the problem. And if it's something you need to, if it'll give you the steps to fix it, great. If you need to engage with tech support, it gives you, a lot more information to start with than just something happened and I need help. Kind of help you get fixed a lot quicker. Occasionally, you'll get the situation where someone will say, everything was working yesterday, but, I came in. Or, I swear we didn't do anything, but something happened. A lot of times, stuff happens. Or maybe you're just, you were kind of going in to change the service and you fat-fingered something and you deleted a component. What was it supposed to be? And if you try and call in for support and try and get help, the first thing they're going to say is, great, cool. Did you make a backup of your configuration? And you'll say, yeah, I did. It was like, let me look. Oh, yeah, I got one here from like 6 months ago. So you're either going to have some really uncomfortable times where you're trying to remember everything you did in the last 6 months. But thankfully, if you're using GeoEvent Server 10.5 or newer, we actually make a backup for you. This is something that we kind of do behind the scenes. If you go into the global settings, the very first setting up there is an automatic backup setting. So by default, every night at midnight, we do an export of the configuration. This does not include all the data obviously flowing through, but this is just an XML configuration of how the service is configured, all the inputs, all the outputs, all the components, exactly how it's run. We will keep up to 10 days of that, but you can certainly change it. You can change what time it's updated. You can change the max volume of these. And this is configured through a folder called the Automatic Backups folder, which is in the data store, which is listed there in the data store. By default, this will write out to the local file path, program data, Esri GeoEvent. Although we had a great recommendation earlier in the week that said, well, what if my machine fails and I need to get my configuration? The default settings are writing to that machine. So, I think definitely in the future as we offer this session, we'll had to recommend move that somewhere else, point that setup to another location.
Yeah, you can use an NFS mount or a Samba mount. You can put that address in there and it'll work just fine, but we'll be adding Azure Blob and S3 at 10.7.
So with that kind of wraps up what we have for you guys for best practices. We hope this information is useful. We have a lot of new material in here today. This will be available hopefully in a few weeks within the proceedings.esri.com site. And we always welcome your feedback as well. So for those of you using the Events app, please go in and submit your feedback. Let us know if there was information you wish we had covered, or if we need to modify the delivery mechanism in any way. I mentioned before we're going to have the Proceedings site. But with that, I'll kind of open it up for you guys for questions, if there's any at this point.
We have plenty of time for questions because we're the last session of the Dev Summit. So. Was this useful? Yeah.
Good stuff. Yeah, it's unfortunate. We like these sessions. It's a great way to just put information that is sometimes a lot of it is in the help, but sometimes it's a little trickier to find. And just these kinds of sessions let us kind of cut through a lot of the process and just kind of say, hey, make sure you're doing this or don't do this. So hopefully it's useful for you. All right, well, thanks everybody. We'll hang out for a few minutes if you guys have any follow-up questions.